This is an example of how to calculate the volume of a parallelepiped that is determined by these three vectors. We're also going to be looking at this from the perspective of GeoGebra. As you can see, we have the three vectors that are graphed in GeoGebra. We have our A vector defined to be 1, 3, 3. So here is vector A coming up and out of here. Our B vector, negative 1, 1, 3, and B vector is coming up and out of this, and C vector is also illustrated here. So we're looking for the parallelepiped that is going to be determined by these three vectors. I'm going to turn on a couple more vectors here so that we can actually see the parallelepiped coming out. So we've got another vector here that is parallel to C, and let's turn on a terminal point there. Another vector that is going to be parallel to that A vector again, and let's turn on some terminal points out here, and we'll just continue to build the parallelepiped by turning on the vectors that create that volume. So after turning on all those vectors that create that three-dimensional object, we get something that looks like this, right? This is the parallelepiped. That is the object whose volume we are searching for, is the parallelepiped that is determined by the vectors A, B, and C. And so now we're going to calculate that volume, and we'll use the formula that is the formula for the volume of a parallelepiped, which is the absolute value of two of the vectors crossed dot the third. This is inside these absolute values is called the scalar triple product. So we're essentially taking the absolute value of the scalar quantity that we get from the scalar triple product. Well, the first thing that we'll need to do is to calculate the cross product of two of the vectors. Now, as a reminder, we're going to calculate a 3 by 3 determinant, a theoretical determinant again, with the first row is going to be our first vector, so that's 1, 3, 3, and the second row is going to be determined by the second vector, so negative 1, 1, and 3, and then we'll calculate this determinant. So what we end up doing is we take the I vector and we multiply it by the 2 by 2 determinant of the matrix that would remain if we canceled out the row and column that contains the I. So we'll have 3, 3, 1, 3 that is left. And then we subtract the J vector times the 2 by 2 determinant of the matrix that would remain if I eliminate the row and column that contain J. So that's going to be 1, 3, negative 1, 3, closed determinant, plus the K vector times the 2 by 2 determinant that would remain if I were to cancel out the row and the column that contain K. So that's going to be 1, 3, negative 1, 1. So now we have the I vector is going to be multiplied by the determinant of the 2 by 2 matrix is going to be the product of these two terms. We've got 3 times 3, which is 9, minus the product of the elements on the other diagonal, which is 3. And then we subtract J times the determinant here is going to be 1 times 3, which is 3, minus 3 times negative 1, so that's going to be minus a negative 3. And then we have plus the K vector times the determinant here is the product of the main diagonal, which is 1, minus the product of the other diagonal, which is negative 3, so minus a negative 3. And then we just need to simplify this. So A cross B is going to be I times 6 minus J times 3 plus 3 is also 6, plus K times 1 plus 3 is going to be 4. And now I'm going to switch this over to pointy bracket notation so that it's not quite so cluttered looking. So we'll say this is going to be 6, negative 6, and 4. And again, this is our A cross B vector. Remember that we're always putting vector hats on top of any variable that represents a vector. So now we're going to take our A cross B vector and we're going to dot that with our C vector to get the scalar triple product. So A cross B, again, we just calculated that, is 6, negative 6, and 4. And we're going to dot that with our c vector, which back up here was 5, 1, 2. So we're dotting it with 5, 1, 2. And then we calculate this dot product. So a cross b dot c is going to be the x component multiplied by the x component, so that gives me 30. And then y component times y component is negative 6, so we're looking at 30 plus a negative 6 or minus 6. And then we're going to add that to the z components multiplied together, and that's 8. So we've got 30 minus 6 plus 8. So that's going to be 24 plus 8, which is 32. And this is going to be the scalar triple product. Now remember, this scalar triple product could have turned out to be a negative quantity. It is possible to get a negative quantity when we dot product two vectors together. So the volume should be, well, we'll just make sure that it's well known that we would be then taking the absolute value if that turned out to be a negative quantity. But it turned out to be positive on its own, so we'll just go ahead and say that the volume is 32. We don't know what the units were, but let's just call that units cubed, because we are referring to the volume of a three-dimensional solid.